So the first method for finding inverse Laplace transforms depends on finding expressions in the table of Laplace transforms and then looking up what the corresponding function of t is. So for instance, when we have to find the Laplace inverse of 5 over s minus 6 minus 6s over s squared plus 9 plus 3 over 2s squared plus 8s plus 10, we can split that up into three pieces because of linearity. And in fact, we can split this up as 5 times the Laplace inverse of 1 over s minus 6 minus 6 times the Laplace inverse of s over s squared plus 9, and then plus 3 times the Laplace inverse of 1 over 2s squared plus 8s plus 10. So all I did was use the linearity of the Laplace inverse transform. And so now we want to match this up. So if we look at 1 over s minus 6, the closest form here in the table of Laplace transforms is 1 over s minus a. So when we match that up in this example, we see that a equals 6 when we compare that with 1 over s minus a. And so that Laplace inverse is e to the power at, with a being 6. So this Laplace inverse is e to the power 6t. And then we still have that 5 in front. So for the second expression, the s over s squared plus 9, we want to compare that with this expression right here, s over s squared plus b squared. And what we see here is that b, the s squared plus b squared, b equals 3. And so this is when we compare that with s over s squared plus b squared. And so our second part of our solution is minus 6 times, and that's cosine of bt. So that part is cosine of 3t. Now, the last one is a little bit harder because when we look at s squared plus 8s plus 10, there is no corresponding value there. So what do we compare this with? Well, we have to compare this with maybe one of these right here, because we have a quadratic expression in the denominator, and we have, in our case here, we have a constant in the numerator. So we're going to compare this with this right here. So we want to compare this right here. Now, in order to do that, we have to complete the square in order to compare that with this expression here. So the easiest way to complete the square here is to first factor out a 2. So I'm going to write this as plus 3 over 2 times the Laplace inverse of, and then I get 1 over s squared plus 4s plus 5. And now I'm going to complete the square. So I'm going to take this expression here, and I'm going to complete the square. So in order to complete the square, I'm going to take half of this. So that's plus 2. And then I'm going to put s there. So I have s plus 2 squared. And then I have to subtract the extra term that I introduced. And so I take minus 2 squared. And then I still have the plus 5 from before. So at first, you only look at s squared plus 4s. You take half of the plus 4. That becomes plus 2. And then s plus 2 squared minus 2 squared is the s squared plus 4s. And then we still have the plus 5. So when you simplify that, this expression right here becomes 1 over s plus 2 squared plus 1. Negative 4 plus 5 gives us positive 1. And so now when you compare that with this expression right here, right, so I'm going to compare that with this. I see that b equals 1 and a equals negative 2. So my solution for this part is then e to the power at. So that's e to the power negative 2t. And then sine of bt. So that's sine of t. And my entire solution then is given by 5e to the power 6t minus 6 cosine of 3t, and then plus 3 over 2 e to the power negative 2t sine t. So that is the inverse Laplace transform of this expression. So let's do one more example like that, and then we'll move on to somewhat more sophisticated methods. So let's find the inverse Laplace transform of 5 over s plus 2 to the power 4. So now we have to compare that with something in our table here. And so we're going to compare this to well, the closest here would be something like this. So we're going to compare this with n factorial over s minus a to the power n plus 1. That's in the table, and the corresponding inverse Laplace transform of that would be e to the power at t to the power n. So now let's take a look and compare. So the first thing we want to do is either look at the plus 2 or the power of 4. Let's take a look at the plus 2, and you compare that in the expression with negative a, and we see that negative a equals 2 or a equals negative 2. Then the second part that we want to compare is the power 4, and we want to compare that with n plus 1. So we see that n plus 1 equals 4, and so n equals 3. Now, that leaves a little bit of a problem here, because when we plug in 3 into this formula here, we get 3 factorial, and that's 6, and we have 5 there. Now, that's not a real problem, because we can always multiply our answer by a constant coefficient, and that will take care of that discrepancy. So let's summarize what we found here. So we know that the Laplace inverse of, so very general, the Laplace inverse of n factorial over s minus a to the power n plus 1, that is e to the power at t to the power n. In particular, the Laplace inverse of 3 factorial over s plus 2 to the power 3 plus 1, and I guess I should write minus 2 here. That Laplace transform is e to the power a, which we found to be negative 2 t, and then t to the power n, that's 3. Oh, and I forgot my factorial here. So that's 3 factorial, or 6. So the Laplace inverse of this is this. And so we're almost there. We have a 5 instead of a 6 here. So when we have to find the Laplace inverse of 5 over s plus 2 to the power 4, I'm going to write that as the Laplace inverse of, and I'm going to just multiply this by 6. So I'm going to take my 5, and I want a 6 there. So I'm just going to multiply that by 6, and then I'm going to divide by 1 over 6. So I'm going to get the same value, same expression, and then I divide that by s squared, or s plus 2 to the power of 4. And I want to keep that 6 because that's what I have here. And so what I take out is 1 over 6 times 5. So I have 5 over 6 times the Laplace inverse of 6 over s plus 2 to the power 4. And that's 5 over 6 times the e to the power negative 2t, because my a is negative 2, and then my n is 3, so times t cubed. And that's my final answer for my Laplace transform.